Last time, we worked through the major concepts that underlie molecular orbital theory, and eventually got to the point where we could build an energy level diagram that represents the orbitals in a diatomic molecule. This time, as promised, we're going to look at a few examples of using these diagrams in practice. Let's start simple, and build a couple of homonuclear diatomic molecules. That is, molecules composed of two atoms of the same element. Nitrogen gas is one example of these, and we could start here by simply filling up an orbital filling diagram for the atomic orbitals of the two separate nitrogen atoms first. We'll focus here on drawing just the valence shell orbitals and skip the 1s orbitals for now. This is often done, actually, because none of the core molecular orbitals are going to affect any of the properties we're seeking to reveal here. But after you finish the video, you should try drawing them in too, just to confirm this for yourself. Since we're only considering the valence shell here, we have 5 valence electrons each to distribute into our atomic orbital filling diagrams, and the layout would look something like this. Now we're going to construct the molecular orbitals in the center. If you want to review where all these molecular orbitals are coming from, go watch the previous video in this series. The only trick here is to remember the relative energies for the bonding orbitals in this part of the diagram. For dinitrogen, as well as for other homonuclear diatomics lighter than dinitrogen, the pi bonding orbitals come first, followed by the sigma bonding orbital. Now all that's left to do is take all the electrons in the outer columns of the diagram, pool them all together, and use them to fill up the middle of the diagram. We have 10 total electrons to distribute, so our finished diagram should look something like this. For the moment, there are two major things we can take away from this diagram that we put so much work into. The first is a calculation of bond order. When we were drawing Lewis structures earlier, we also had this concept. The bond order increased from single to double to triple with each electron pair that you shared between the atoms. Here it's the same idea, we just have a more complete picture now of how those sharing interactions are actually laid out. All the electrons in bonding orbitals behave as though they're being shared between the atoms. Remember that all the bonding orbital shapes bridge the two atoms together, and more importantly, since they all have lower energies than the individual atomic orbitals that formed them, both atoms get an energy advantage for every electron that goes into one of those bonding orbitals. On the other hand, antibonding orbitals exhibit all the opposite traits. Spatially, their electron density is divided by a node along the bond axis, and since their energies are all higher than the original atomic orbitals, each electron that a molecule has to put into an antibonding orbital represents an energy cost. So bonding electrons contribute to the strength and stability of the bond, while antibonding electrons take away from that stability. Using these ideas, we can write a simple formula for bond order and calculate the answer by adding up the number of bonding and antibonding electrons that we see in the diagram. For our nitrogen molecule, the answer comes out to be 3. So incidentally, this agrees with the triple bond that we find in our Lewis structure representation of N2. The second major observation harkens back to a simple test that we performed on single atoms earlier in the year. If you wanted to know whether an atom or ion was paramagnetic, and that is strongly attracted to a magnetic field, all you had to do was look at an orbital filling diagram and see if you had any unpaired electrons. Unpaired electrons indicates paramagnetism, while a structure with complete electron pairs in every orbital meant that you had a diamagnetic substance, something that doesn't respond much to a magnetic field. We can do the same quick check here for molecules, now that we have an accurate picture of how the molecular orbitals are filling. One glance at our nitrogen molecule shows us that all the occupied molecular orbitals are filled, so N2 is diamagnetic. Okay, so let's apply these tests to another simple example, molecular oxygen. Things look pretty similar in the diagram, except that we have 6 valence electrons in each atomic orbital set, and the pi sigma order is swapped from what we saw in our previous example. This time, when we fill the molecular orbitals with our pool of 12 valence electrons, we're going to end up with a couple of unpaired electrons up in the pi antibonding orbitals. Remember to spread them out like we do when the orbitals have the same energy. This time, our calculation gives us a bond order of 2, which also happens to agree with the Lewis structure, and one little glance at the diagram also tells us that this molecule is paramagnetic, thanks to those aforementioned unpaired electrons. Now let's try a heteronuclear example, nitric oxide. This is the first time we've seen two different atoms bonded in this context, and you'll notice that the diagram looks a little lopsided. The atomic orbitals of more electronegative atoms always have lower energy, so oxygen's side of the diagram sinks down a little more than its bonding partner. This time, when we fill up the diagram with the 11 valence electrons we have on hand, we end up with a single unpaired pi star electron. So we can tell right away that nitric oxide is expected to be paramagnetic. But it also means that our bond order calculation isn't going to give us a whole number this time. This is the first example that deviates from how we might have drawn the Lewis structure. Following all of our normal rules, your Lewis structure would end up with a double bond between the nitrogen and oxygen, but from this molecular orbital diagram, we calculated a bond order of 2.5, making it actually a little shorter and stronger than our Lewis structure would have predicted. The real bond length, determined by physical experiments, is also shorter than a typical NO double bond, which shows that molecular orbital theory is giving us a superior representation here. Next up, we have a series of heteronuclear compounds of carbon and nitrogen, with various charges. We'll use all of our normal rules to fill each of these examples at once, and the only thing to point out here is that I've chosen to take an electron away when needed from the less electronegative atom's side, and give an extra electron when needed to the more electronegative atom's side. Since we really just care about the molecular orbitals in the middle of each of these diagrams, this is a very minor consideration. Based on the resulting diagrams, it looks like only one of our compounds, the cyanide ion, is going to be diamagnetic. And according to the bond order calculations, this compound is also the most stable version of this pairing, with a solid bond order of 3. Speaking of stability, there are several factors that go into making a molecule energetically stable, but the simple bond order calculation is a good first test. If you ever end up with a calculated bond order of less than 1, like this diatomic helium example, you know right away that the compound is unlikely to form in nature. The diagram clearly shows in this case that there's no net energy advantage in having two helium atoms hang out together like this. One last example, and this one's a bit weird. We're looking at a molecular orbital diagram of hydrofluoric acid, and you might be thinking that we're setting it up wrong. But remember what we said earlier about electronegative atoms having lower energy associated with their atomic orbitals? That's actually what's happening here. The 2s orbital of fluorine is still here, but fluorine is so much more electronegative than hydrogen that it's actually the p orbitals of fluorine that are most closely matched in energy to hydrogen's 1s orbital. Atomic orbitals that are close in energy can combine to form molecular orbitals, so let's take what we've got and see what we can do here. If the s orbital from hydrogen overlaps head-on with one of the p orbitals from fluorine, and I guess that would have to be the one that's oriented along the bond axis here, we could get a sigma bonding and antibonding pair. After that, though, we're actually done, because hydrogen doesn't have anything else to combine with the other two p orbitals. Those p orbitals are going to end up in our final diagram just as they originally were, as non-bonded orbitals. Fluorine's 2s orbital will end up that way too. Here's the finished diagram, and incidentally, there are actually some analogies we can draw to the Lewis structure representation of this molecule. The single bond drawn in the Lewis structure represents those 2 electrons in our sigma bonding orbital, and the 3 lone pairs drawn on fluorine could be the 3 pairs of electrons in this diagram that are still living in fluorine's non-bonded orbitals. It's not always going to work out like that. In fact, many of our examples in this video don't really jive as neatly with how the lone pairs are drawn in their corresponding Lewis structures. But this is one example showing an unusual case where several pairs of electrons really do end up localized on a single atom in the bonded pair. That's where we'll leave it for now. Thanks for watching.